All right, hello and welcome back to group theory. So today we're going to be talking about subgroups mostly, and also at the end we're going to briefly mention direct product groups. So the idea behind both is taking groups that we know and finding other groups. Subgroups, we're going to be finding groups inside the groups we know, and direct product groups are like taking two groups that we're familiar with and then making a third out of them. Alright, what is a subgroup? A subgroup is just a subset that is itself a group. So recall that G, if G is a group, is a set endowed with a binary operation. So it makes sense to talk about subsets of a set under the same operation. And if it turns out to be a group itself, then we call H a subgroup of the group G. We often denote subgroups H subgroup of G. We use the less than symbol, if you will. Alright, so how do we tell if H is a subgroup of G? Are all subsets of G subgroups of G? Well, the answer to that is no. Think about the axioms of a group, right? We need it to satisfy all three in its own right. So we have associativity, it has to have an identity, and it has to have inverses. And I'm going to write for here, it has to be closed. Usually this is just implicit, but it's going to be more relevant when we start talking about subgroups, because maybe there are things which satisfy associativity and an identity, but which are not closed. Alright, so let's think about this. Well, if we're talking about the same binary operation, so if A star B star C is equal to A star B star C, for all elements A, B, and C in the group G, then since all elements in the group, well, the one we're testing, the set H, are also in G, it must also be true that multiplication is still associative. So associativity automatically carries over from a group to any subset of that group. Alright, what about the identity? Well, it's not true that any subset of a group is going to contain the identity, right? I mean, it's one element. So we're definitely going to be looking for subsets which contain the identity. Now what about 3? Well, we can't just pick some random subset that also has the identity, because every element won't necessarily, its inverse might not be in that subset. So we have to make sure that the inverses are in that subset. And even though I mentioned it last, it's probably the most important that we first check closure under the binary operation, right? Just because A star B is going to be in the group G for any A and B in the subset H doesn't mean that that product will end up being in H, right? We could have, to draw this, we could have H here and G here, and A and B are both in there, but then somehow A star B is in there. Or better yet, suppose A star B is in here, we could still have B star A out here. If A star B and B star A are not equal, in other words, if the group is not abelian, we could have something like that even happen. Alright, so what it's looking like is for H to be a subgroup of G, we need to check that it has an identity. Well, the identity, there's only one identity, we proved that before. It needs to have inverses for all the elements in there, and it has to be closed under the binary operation. Now at this point you might actually see that if we have closure under the binary operation and we have inverses, that these two imply that the identity has to be in the group. Why is that? Well, if we know that for any A and B in the subset H, A star B is in H, then we know that inverses are in H, so A inverse is in H, then A star A inverse by literally just these two properties, must also be an H. But what is A star A inverse? That's just going to be the identity, E. So if we have inverses and we have closure, we have an identity. And we already said associativity naturally follows over. So it turns out all we have to check is that the subset H has inverse elements and it has closure under the binary operation. But wait, there's an even more efficient condition if you really want to be quick about things. You can combine both these conditions into one condition by demanding that for all elements A and B in the subset H, we want A times B inverse to be an H. In this statement, we have that B inverse has to be an H because we need, what if B is equal to A? Well, if B is equal to A, then that's going to be the identity, so the identity has to be in there. Great. So then if A is equal to E, then we have E star B inverse has to be an H, and that's just B inverse. So together, wrapped up into this one condition, we have both of these properties, which we said implies this, and this is automatic. So this is the subgroup test. Okay, this is what you're going to apply if you want to figure out, does the subset H of a group G form a subgroup? You ask for all elements in the subset, is A times B inverse in that subset? If that's true, then H is a subgroup. All right, now let's look at a few important examples of subgroups. All right, the first one would be Z plus and R plus, the additive integers in the additive real numbers, right? So if we take all the real numbers under the operation of addition, then all the integers, so negative k to 0, 1, 2, k, etc., these are going to form an additive group that is contained in the larger group, which is the real numbers under addition. It should be fairly straightforward. But just for kicks, let's apply the subgroup test. So if we have some m in the integers and some n in the integers, the question we want to ask is m minus n also in the integers. And I say m minus n because in additive notation, recall, n inverse, if we have an additive group, is just written negative n. And the answer is going to be yes. Any integer minus another integer, still an integer. That should be fairly self-evident. So that this is indeed a subgroup of the additive real numbers. Now here's a group that we didn't talk about before. So we talked about the real numbers under addition. How about multiplication? Well, if you include the number 0, things are going to go awry. So what we do is we consider the real numbers without. This means this set without this set. So the real numbers without 0 is going to form a multiplicative group, as a matter of fact, because any two real numbers multiply to another real number. Specifically, any two non-zero real numbers multiply to another non-zero real number. And all of these have a multiplicative inverse, so that if x is a real number, 1 over x is also a real number, with the single exception of 0, which is why we take it out. And this is going to be a multiplicative inverse. X times 1 over x is just 1. And in this case, no longer is 0 going to be our identity, but 1 is going to be our identity. Alright, so now let's consider the real numbers without 0 inside the complex numbers without 0. The question is, if we have two real numbers that are not 0, is it true that A times B inverse, which in this case is 1 over B, is this going to be, once again, a non-zero real number? So in other words, is A divided by B a non-zero real number? And the answer is yes. So it passes the subgroup test. And of course, implicitly here, I'm telling you that this is a group to begin with. The complex number is under multiplication. This means considered under the operation of multiplication. All right, here's a more interesting example. How about modular arithmetic from before? So suppose we have Z6. All right, what is Z6? We can think of it as 0, 1, 2, 3, 4, 5, and then just loops back, right? It's going to be addition modulo 6, right? Divide by 6, figure out what the remainder is, and of course we're only considering integers. So what about this? Does this have any subgroups? Yes, as a matter of fact. All right, suppose we look at the subset 0, 3. And once again, this is going to be under addition modulo 6. Well, 3 here is its own inverse. 3 plus 3 is 6, which mod 6 is just 0. So it is its own inverse because 3 plus 3 here is 0, and 0 plus 0 is 0. 0 plus 3 is 3, 3 plus 0 is 3. So clearly this is closed and is its own group. All right, now let's consider the subset 0, 2, and 4. Again, addition mod 6. Well, 0 plus 2 is 2, 0 plus 4 is 4, 0 plus 0 is 0, 2 plus 2 is 4, and 2 plus 4 and 4 plus 2 are going to be 6, which mod 6 is 0. So this is going to be closed, and 4 and 2 are going to be inverses of each other, and 0, as always, is going to be its own inverse. Thus, we are going to have inverses, we have the identity, it's going to be a subgroup. Now, if you're looking closely, you might notice something here, that we have mod 6. Now, if you're paying attention, you might notice something interesting here. So 6 is equal to 2 times 3. So we have our group, which has 6 elements in it. By the way, this number of elements in a group is called the order of a group, and it's denoted, in this case, with these lines around it. Just one line, but I tried to make it thick. Just like absolute value signs. The order of a group is the number of elements in it. Okay, well, the order of this group is 6, and 6 is divisible by 2 and 3. But if you'll notice, we had a subgroup with 3 elements and a subgroup with 2 elements. Is this a coincidence? Well, suppose instead we had Z10. Z10 is going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you are going to find that the only subgroups of this are going to be 0, 5 and 0, 2, 4, 6, and 8. Once again, we have that 10 is equal to 2 times 5. We have a subgroup of order 2 and a subgroup of order 5. And we're going to figure out how the orders of groups and subgroups are related later. But for now, let it suffice to say, for the special case of addition mod P, that if M divides P, then Zm is going to be a subgroup of Zp. And in fact, this even works in the trivial case. But perhaps it already dawned on you that the element just 0 by itself is going to satisfy the axioms of a group, right? 0 plus 0 is 0, and 0 is its own inverse, and 0 is the identity. And this is true, that there are 2 subgroups which are called trivial subgroups of any group, and that is going to be the group which is the group itself. So H is equal to G. And to distinguish between groups that subgroups that don't include the mother group, we say proper subgroup. So just as we would say a proper subset of a set is not the same as that set, right? It's any selection of the elements that is not the whole thing. So we're going to say that any subgroup of a group G which is not equal to G is a proper subgroup. Now of the proper subgroups, we still have one more trivial group, and that is going to be the group with just the identity element. It is always a group. So you're going to see that 1 divides P for any P, and we always have the trivial subgroup. We always have that P divides P, so that we have the other trivial subgroup, which is the group itself, right? And then any additional factors, like in the case of Z10, we'll have Z2 as a subgroup of Z10, and Z5 is a subgroup of Z10. And the why of this will come later. All right, next example. Suppose we consider all mappings from the set 1, 2, 3 to itself. So this is going to be a special case of what I called the automorphism group before. So what are all the possible mappings here? Well, there's going to be 1 to 1, 2 to 2, 3 to 3. That's going to be the identity mapping. So we'll call that I. There's going to be 1 to 2, 2 to 1. We'll call that A. We'll do the switching of these two. Well, that one stays the same. We'll call that B. And we'll call C the switching of those two elements while 2 stays the same. So, do we have any others? Yes, we do. We could go 1 to 2, 2 to 3, 3 to 1. We'll call that D. And we could do, let's see, the opposite direction, right? So 2 to 1, 3 to 2, and 1 to 3. And we'll call that E. So this is called S2, this group, or sorry, S3, because it is a set of all permutations on 3 symbols, or the set of all mappings of a 3-element set, bijections specifically, to itself. Now, when I first introduced the automorphism group, I told you about the case where we had just 2 elements, right? So 1, 2 to 1, 2, and I said, how many mappings are there? Well, you can go 1 to 1, 2 to 2, or you can go 1 to 2 and 2 to 1. So there's only 2 mappings. But what you'll notice here is that if we demand that 3 goes to 3, then we have 2 options, 1 to 1, 2 to 2, or 2 to 1 and 1 to 2. And this is precisely because S2, the set of all bijections from a set with 2 elements to itself, is a subgroup of S3, the set of all bijections of a set of 3 elements to itself. We'll talk more about this. The reason we use S is because it's also called the symmetric group. So we'll talk more about this later, but it's a great example of a subgroup. And it's true, in fact, that S sub k is a subgroup of S sub n for any k less than n, where we're using this symbol to mean 2 different things, right? Subgroup of and a number which is less than a number. So GL of n has many, many interesting subgroups, very interesting subgroups, but there's one I want to draw your attention to right now, and that's called the special linear group. So the special linear group, or SL of n with real entries, is going to be defined to be the set of all matrices in the general linear group such that the determinant of M, we also use these lines to mean determinant in linear algebra, right, is equal to 1. How do we know that this is going to form a subgroup? Well, let's do the subgroup test. All right, So let's assume matrices X and Y are in the special linear group. Then what we want to do is show that the determinant of the product X times Y inverse, we know that Y has an inverse because it's in the set of all invertible matrices. It's in the special linear group, which is a subset, at least until we prove it's a subgroup, of the general linear group, right? So Y definitely has an inverse, and we want to look at this product, and we want to show the product is in here, right? That's a subgroup test. And to do that, all we have to do is show that its determinant is 1. Well, I'm just going to use a fact from linear algebra, which is that the product of, the determinant of a product is equal to the product of the determinants. And then a second fact, which is that the determinant of an inverse is equal to 1 over the determinant of the matrix. So that this is determinant of X divided by the determinant of Y. But since X and Y are both in the special linear group, their determinants are just 1. So this is equal to 1 divided by 1 is equal to 1, and so this product, XY inverse, is definitely in the special linear group. And so it passes the subgroup test, and it is a group, a subgroup of the general linear group. All right, now I'd like to show some facts about subgroups. All right, I'd like to now prove a theorem which says that if H is a subgroup of a group G, and if K is another subgroup of the group G, then the intersection of H and K is itself a subgroup of the group G. All right, this proof is going to be really straightforward. So by the subgroup test, we know that since H and K are both individually groups, that A and B, for all A and B in H intersect K, by definition this means that A and B are in H and A and B are in K, right? Now since H and K are both subgroups of the group G, we know the product AB inverse is going to be in H, right? That is the subgroup test. Likewise, we know that AB inverse has to be in K because K is also a subgroup. Well, now we've shown that this product is in H and it's also in K, then by the definition of H intersect K, we have that AB inverse is in H intersect K. And thus, by the subgroup test, H intersect K is itself a subgroup of group G. Alright, I'd also like to tell you about something called the center of a group. It's an important subgroup. So the center of a group G, which I'm going to denote C of G, is going to be equal to all the elements A in G such that AX is equal to XA for all X in G. Groups for which the commutative property always holds are called abelian groups, but a group need not be abelian. But there is an important subgroup such that each element commutes with every other element of the group. And this is called the center of the group. Let's prove that it is indeed a subgroup of the group G. Alright, now we know that for all A and B in the center, by definition, AX is equal to XA and BX is equal to XA for all elements X in the group G. It commutes with every element of the group G, even if G is not a commutative or abelian group. Alright, so we want to do the subgroup test. So we want to consider, does AB inverse times X equal to X times AB inverse? If this is true, then AB inverse is in the center, and thus it's a group by the subgroup test. So, let's consider this product. Well, by the associative property that holds in G, we're going to have this to be true, right? This is our product. Well, this can be written because the inverse of a product is the reverse order product of the inverses. This is going to be equal to A times X inverse B inverse, where we know X inverse exists because it's in the group G, and likewise with B being the inverse of the inverse. So then, but B, we assumed B commuted with all other elements in the group G, so that this is equal to B X inverse. But then, of course, the inverse of a product is the product of the inverses in the reversed order, is equal to B X inverse, which is just X, times B inverse. But we know that AX is just equal to XA for all X in the group, so that if we take out this parenthesis and put it here, we have exactly what we were trying to show, that this element A times B inverse is equal to, or times X is equal to X times the element A B inverse for all A and B in the center of G, and thus by the subgroup test, the center of a group is itself a subgroup. All right, now I'd like to talk about direct product groups. And this is going to be sort of, but not quite, the opposite of subgroups. Subgroups, we were intuitively trying to find smaller groups inside our groups. And now we're going to turn our attention to building bigger groups out of the groups we already know. So if I have two groups, G and H, then the direct product of G and H, denoted like this, a multiplication sign inside a circle, is going to be the set of all coordinate sort of vectors, well, I don't want to say vectors, but coordinate pairs of GH such that G is in the group G and H is in the group H, where we're going to have an operation defined on this set, defined in the following way. So if star is the operation in G, say that H has the operation of different kind of star, so asterisk and 5-point star here, then the operation on this set that we're going to consider is G1, H1, I'll just use the same symbol as this for now, times G2, H2 is going to be defined as the pairwise products according to their own groups. So G1 asterisk G2, and then for the second coordinate, if you will, H1, 5-point star here, H2. And this is how we're going to define our operation of two of these pairs. All right, so the question is going to be, is the direct product a group? The answer is yes, but we have to prove it. So let's use the three group axioms. First, we want to say, is it closed? So I'll just put a little 0 here. So do we have closure? Well, so for all G1, G2 in the first group, G, and for all, well, my handwriting is terrible, and for all H1, H2 in the second group, it's true that, defined how we just defined it, that G1, H1 times G2, H2 is going to be equal to G1 asterisk G2, H1, and then whatever multiplication operation it has, times H2. Now, just by looking at this, we know that G1 star G2 is another element of G because G is a group and thus must be closed. So that's another element of G. And then H1 star H2 for the same reason is also another element of H. So that we get that the product is another element of G direct product H. So we know it's closed. All right, now the three group axioms. So first we want to show that there's associativity. So if we have G1, H1 times G2, H2, and then that's in parentheses, and this is times G3, H3. This is going to be equal to none other than, we have to do this one first, so this is going to be G1 star G2, H1 star H2 times G3, H3. Well, this is going to be just equal to G1 star G2 star G3, H1 star H2 in parentheses star H3. And now by the associativity of G and the associativity of H, we're going to have this is equal to G1 star G2 star G3, right, where we switch the parentheses, and then H1 star H2 star H3, where once again we switch the parentheses because even if we don't know yet if this direct product is a group, we know that G is a group and we know that H is a group. So it's got to hold. So now kind of working backwards, we get that this is equal to G1 H1 times G2 star G3 H2 star H3 is equal to none other than G1 H1 times, and then in parentheses, G2 H2 times G3 H3. And this is exactly what we wanted to show, that we can change the parentheses from here to here in the direct product group, and it's still, it's equal, right? So there's associativity. Group axiom number 1 is satisfied. Axiom 2 is going to be the identity. Does this direct product set, or this Cartesian product, if you like, equipped with the binary operation, the way we defined it, does it have an identity element? Well, consider this. Let's call E sub G the identity in G, and then E sub H the identity in H, right? So then let's consider the pair E sub G and E sub H. Well, so for all pairs GH in the direct product G cross H here, we're going to have that GH times E sub G, E sub H is going to be equal to G star E sub G, H star E sub H, right? But we know that this is just going to be pairwise is equal to G and H, right? Because G is a group, H is a group. And we're going to have the same thing going the other way, that if we have E sub G, E sub H times GH, this is going to be equal to E sub G star G, E sub H star H. This is going to be equal to GH. Now because of this, we know that for any arbitrary element of the direct product group, we're going to have this times the identity is equal to the identity on the left times this is equal to just that element. So it is, this E sub G and E sub H is indeed an element which serves as an identity for our direct product. So does every element in the direct product set have an inverse? So, well, we know this. Suppose we consider for all GH in G cross H, suppose let GH inverse equal to G inverse, H inverse, where this is the inverse of element G in G, and this is the inverse of H in the group H. Then what are we going to get? We're going to get that GH times G inverse H inverse, or rather, the way I'm defining it, this is the inverse element, is equal to GH times G inverse H inverse. is equal to G star G inverse H star H inverse, and this is just its inverse in G, so we know this is equal to the identity in G, and this is likewise going to be the identity in H. And of course, we can do the same thing on the other side. So if this is the way we define an inverse, then inverses are going to be contained in the direct product. And so it's closed under the binary operation and satisfies all three group axioms. That means that our direct product boy or girl is going to be a group. All right, for our first example of a direct product group, I'd actually like to introduce a new group to you. So I'm going to define SU of 1 as the set of all elements e to the I theta such that theta is in the real numbers. Now e to the I theta, if you have not seen Euler's formula before, it says that if I is the square root of -1, the imaginary unit, that the exponential of I times some real number theta is equal to the cosine of theta plus I times the sine of theta. You can check out my video on Euler's formula if you want to see a derivation of that. But basically we have cosine theta is going to be the real coordinate, sine theta is going to be the imaginary coordinate. So if we think of this as x and y, it's going to trace out the unit circle. So we can think of SU of 1, or the special unitary group in dimension 1 dimension, as the unit circle in the complex plane. This is 1 here, this is I, this is -1, and this is -I. I'm assuming you're familiar with the complex plane. All right, well, we can actually think of every point on this unit circle, also called S1, as an exponential of this form, and they form a group under rotations, right? So that we can look at, say this is e to the I theta, this is e to the I phi, where this angle is theta and this angle is phi, and then we have some other number down here, which is going to be e to the I times theta plus phi. It's the same as rotating by theta and then by phi, or by phi and then by theta. So you can think of this as a rotation in the complex plane, or you can just think of it algebraically like this, and you should know by now that exponentials behave such that e to the I theta times e to the I theta times e to the I phi is going to be equal to e to the I phi plus I theta, or just if you factor out the I is equal to that, right? So you multiply two of these numbers, you get another number of the same form. That's what's important here. Well, we can actually take a direct product here. Let's take the direct product SU of 1 with itself. So SU of 1 cross SU of 1. This is going to be the set of all sort of coordinates, right? E to the I theta, e to the I phi, such that theta and phi are real numbers, right? I told you this special unitary group is a group, so the direct product of it with itself is going to form another group. And actually, this group is kind of interesting in that it essentially describes a torus, right, in space. So that if we have this donut shape, that we could consider this as two circles essentially, so that specifying one real number theta specifies one point on one circle, and then phi gives you a coordinate on another circle, right? And then the two of them will specify any point. You can think of like a little bit of some coordinates here, and coordinate lines, etc. You think of sort of a curvy grid, so that this essentially describes the geometry here, and that you can you can pick out any point in the torus you want by just selecting any point in here. So we talk about this as being a representative of the torus. There's more than one way to sort of express the torus. That's just a cute little example of a direct product. All right, now let's talk about Z2 cross Z2. Now what does this actually look like? Well, if we're thinking of selecting one element from each group, right? So these are going to combine to form a set, which is going to be the coordinate pairs 0, 0, 0, 1, 1, 0, and 1, 1. So it's going to have order 4. We know it's a group already because it's a direct product of two groups. Now, the question is, what's the structure of this group? Again, our element-wise operations are going to be addition modulo 2. In particular, I want to compare this with Z4, right? The set of 0, 1, 2, and 3, where we have the operation of addition modulo 4. They both have 4 elements. Are they the same? Are they essentially the same thing, just kind of represented in different forms? That's the question I want to ask. All right, so to understand this, I've drawn what's called Cayley tables. These are going to be tables where you sort of line up the elements like this, and then the same thing down here in the same order, and then you look at their products. And if it's an abelian group, you're going to see a symmetry, but in general, they're not abelian. And we're still going to talk about it as though it were a multiplication table, even though that operation is addition modulo m, whatever. All operations are multiplication as far as we're concerned. So these are called Cayley tables, and they can tell you a lot about what's going on inside a group. You can always do this just by looking at like symmetries and patterns in the Cayley table. All right, let's start with Z4. It's going to be a little bit easier. So 0 plus 0 mod 4 is going to be 0. Likewise, 0 plus 1, 1, 0 plus 2, etc. So we get that, right? What is 1 plus 1? Well, it's going to be 2. We're going to have 1 plus 2 is 3, 1 plus 3 is 4, mod 4 is going to be 0. And of course, this is an abelian group, so that we're going to get the same thing reflected over here. 2 plus 1 is 3, 3 plus 1 is 0. What's 2 plus 2? It's going to be 4, mod 4 is 0. 3 plus 2, mod 4 is going to be 1. And 3 plus 3 is 6, mod 4 is going to be 2. Okay, so that's our Cayley table for Z4. Now let's do Z2 cross Z2. 0, 0, 0 plus 0, 0. Keep in mind this is mod 2, right? For both. It's going to be 0, 0, our identity element here. Now 0, 0 plus 0, 1, 0, 1. Same thing here, right? 1, 0. It's going to be 1, 0, 1, 0. 1, 1, 1, 1. It's still abelian. All right, now, what is 0, 1 plus 0, 1? Well, the 0 plus 0 part is going to be 0, and the 1 plus 1 part, mod 2, is going to be 0. So this is going to be our identity element, 0, 0. Well, what about 0, 1 plus 1, 0 over here? Well, that's going to be 1, 1. Likewise, 0, 1 plus 1, 0 here is going to be 1, 1. We're going to have 1, 1 plus 0, 1. The first coordinate is going to be 1, and the second one, 1 plus 1 is 2, mod 2 is 0. Similarly, we're going to have 1, 0 here, right? Now, what about 1, 0 plus 1, 0? Well, again, the 1s are going to become 0, mod 2. Then we're going to have 1, 0 plus 1, 1. It's just going to be 0 in the first coordinate. Similarly here, just 0 in the first coordinate. And then what's the last one? 1, 1 plus 1, 1 is 2, 2. Mod 2 is 0, 0. Now, these are both groups with 4 elements in them. This is what I'd like to point out in particular. Now, look at their multiplication tables. This is a great way to tell what their similarities and or differences are, because maybe they just have maybe this is just 2 different representations of the same group, because you can have that, and we'll talk more about that next time with homomorphisms, but that's not what's happening here. Let's look at this. So in this one you have the identity element all the way on this diagonal, and then you have 1, 1 all along this diagonal, and just various other elements, again, symmetric about this sort of diagonal axis here. Now look at this one. Here we have something slightly different. We have our identity element up here, but then we have 3 plus 1, 2 different elements giving us 0. We have 2 plus 2, so 2 is what you'd call idempotent. It squares, or in this case, it plus itself is going to be 0. And then you have 1 plus 3 again, which gives you 0. So we have our zeros right there. And I'd like to point out what's going on here that's so bizarre, and that is that here we have every element is its own inverse, right? Because 0, 1 plus 0, 1 mod 2 is 0, 0. Same with 1, 0, same with 1, 1. Every element is going to be its own inverse. Not so in this group. So it's fairly obvious at this point, these are 2 different groups. So you might think, how many sets of 4 elements could there even be? Not that many that satisfy the group axioms, right? But we have 2 of them here, which are clearly not the same structurally. So we have 2 different groups here. So don't be deceived into thinking that because 2 groups have the same order, that they also have the same structure. And we're going to talk more about how we know whether 2 groups have the same structure or not next time with homomorphisms. So Z4 is going to be the only cyclic group of order 4. And this group is special and has its own name, and it is called the Klein 4 group, because it has 4 elements, but it is not that group. So we have 2 totally different groups. We have the cyclic group of order 4, and we have the Klein 4 group, also abbreviated K4 over here. Interestingly enough, the Klein 4 group is also an a cappella group of math grad students from way back in the day. And they wrote a song called Finite Simple Group of Order 2, which you might have a better appreciation for now. Although my personal favorite of theirs is the 3-body problem.